Hello everybody, welcome. Welcome at 23rd already, Getting Technical live event. And today we have, personally, I think a very exciting subject, and that is model-based machining. And especially the advancements in it, because model-based machining approaches is not something new, but it's something with a high potential for the future. And as always, of course, I'm not alone today. I'm together with Alesia and Margarita. That helps to make this work, all this stuff. And the big challenge I have today is I have only 45 minutes, and the subject itself is so vast, is so wide. For that already here, I would say, if you want to know more about these things, see all the reference materials we have put in the comments if you want to receive information about these technical books. And I make sure that you receive all wanted information. Because model-based machining, there is a bit of a challenge here. Model-based machining means that we want to approach a machining process from a model which is a description of reality, that describes a reality in such a way that we can understand it, that we can control it, that we can influence it. That's the target here. But if we look to the reality of machining, the reality is, and I use two photos here to let you feel a bit what the reality is. The reality to the left is what we call heavy-duty machining. And I think the picture talks itself, what we mean with it. It's machining in situations where, everything is big. And next to heavy duty machining, to the right, we have what we call micro machining. And micro machining is just the opposite. It's the same process, from a physical perspective. But now everything is very small. And model-based machining, the challenge is, can we describe a model that could handle these both situations and everything in between, of course. That's the big challenge. And the risk today, because if you go out on internet and if you try to find information on machining, what you find is, and I think that's a risk, that is that people dive further and further into a machining process. And I just give an example here. What are the cutting forces with orthogonal free dry turning with special treated titanium alloy with a specific tool and specific cutting conditions? They do a lot of testing. And they come with a certain thing, and then the question is, this description of the reality, is this usable outside of the original setting? And that is a bit, the challenge is finding a model that describes whatever reality, and if it's possible, that's another question, but that's the challenge. The risk in trying to find that model is that we lose ourselves into details. And that's what we have to be careful with. Now, what I want to do, and as I said, it's only 45 minutes, but I want to because personally I find this very exciting. Machining physics, applied physics, understanding the process. Because, if you understand the process and then suddenly you have a situation and you think and you come up with what you think should work, do this, do that, and so on, and it works, I think that's exciting. And what I can try to do here is bring over that same excitement to you, that you want to learn more about these things, and all the details we cannot handle, and not in 45 minutes. Let that be clear from the start. Now, if we talk about model-based machining, what is model-based machining? What's the big picture? How do we have to see things? Now, if you look to a machining process we want to control, we want to manage, we want to make sure that it delivers what it's supposed to deliver, and that we have things under control. Now, from a historical perspective, nearly I could say, since ever, the traditional approach is intuition-based machining. Intuition-based machining is a situation where we have an operator, and the guy has experience, expertise, and he takes decisions based on intuition, on Fingerspitzengefühl, we say in German. And that is intuition-based machining. One level higher, the subject of today is that we try to transform that intuition into more objective models, that we try to go away from the subjective approach, I think, I feel, and we go more into an objective approach. It's not about feeling, it's about knowing. And that is what we call model-based machining. And if we continue this journey, because model-based machining, kind of, since we started to use numerical controlled machines, that model-based machining appeared more and more into the picture also. But if you look to the situation of today, we see that people are moving towards sensor-driven machining. Sensor-driven machining is that I measure things, if possible in process. During the actual process, I measure the situation, and we describe it in a couple of minutes what I mean with the situation, but we measure. We compare what we measure with the model which we described previously. We see if there are deviations, yes, no, and if deviations are there and we think the deviations are unacceptable, we modify. Some people call sensor-driven machining also adaptive machining, in the sense of I measure, and based on the results of my measurements, I modify my machining process. Ultimately, it ends into, and I think this is really the future, but I also think the future already started today. It's data-based machining. It's people call it digital machining. I have a model. I have a lot of measurements from my sensor-driven situations. I bring the two together and I create a digital twin of a process, and I use that as a starting point to control the actual physical machining process. That's digital machining in its simplest form defined, data-based machining. Now, intuition-based machining, as I said, that's the origin. It all started there. We were doing machining, and machining is a process we do now since around 150 years, in the modern times, at least I should say. And people didn't really understood from a physical perspective what was going on, and it was trial and error, and people got a feeling of what is possible and not possible. And that's very typical for intuition-based machining. All decisions about how to do it, which tool to use, cutting conditions, improving a situation are based on experience, on expertise of operators. Typical here are trial and error situations. I'm pretty sure you all know it. If you have a new tool and you want to figure out if a new tool will work in a situation, what do? You take a test tool and you do a trial and error. Is it working? Is it not working? What do I modify to make it work? And so on. Intuition-based machining. Historical, where we come from. Today, we try to work more and more, and as I already said, this came a bit with numerical controlled machines, that we said that these machines, it's a bit unacceptable because it's rather expensive machines if you look to the hourly rate. We cannot stand there and try and suppose and think and hope and that type of thing. We need models. We need models to describe. And this became even more important the last 10, 15 years as we saw that the batches of workpieces we had to produce became smaller and smaller and smaller. There was no time anymore for the traditional operator to figure things out. We needed to know as fast as possible how to do, what to do, and be rather sure it works. Now, model-based machining. Machining is a physical process. So if we have a model, the model should describe the physics of machining. The model should, and I give it a title, Applied Machining Physics. We are going to use physical principles, we apply physical principles and try to describe a machining process. Now, a machining process, most of you know it by heart, I suppose, is a process where I have a cutting tool and I make the cutting tool, I bring the cutting tool in contact with workpiece material, with a set of cutting data, cutting speeds and feeds and that type of thing. And I move the tool into the workpiece, I deform the workpiece material, I deform it until it shears off under the form of a ship. And that is the description. There is even a DIN and an ISO norm that describes this. This is machining in the purest form. Now, how the movement of workpiece and tool are relative to each other, that is the typical type of applications we have, turning and milling and drilling, but all of them have in common that there is a cutting edge in contact with workpiece material, deforming it, shearing it off under the form of a ship. And as such, transforming a rough workpiece into a finished, a semi-finished workpiece. Now, if you look to this process, and at previous occasions, we have been talking about this, so for here it's just repeating. If you look to a machining process, it's obvious that there are different types of phenomena. I'm going to deform a material. To deform a material, I need to push against the material, so there is a mechanical aspect in this whole thing. Ships are being formed, and those ships needs to be taken care of. So that's another mechanical dimension. As I'm deforming material, heat is generated, and that heat which is generated is going to have consequences, increased temperatures. That's the thermal effect around the machining process. I'm going to create a certain surface. That's the quality aspect. I have a ship which is in contact with a tool, and there is a gliding process under pressure and so on. So there's going to be some tribological phenomena taking place. So there is quite a multitude of dimensions here we need to take into consideration if we want to describe a machining process. And if we think now on describing a machining process, what exactly do we want to describe? Well, we want, in the end, a result which is a correctly finished workpiece at a certain cost, produced within a certain time. That's the wanted result. And to achieve that result, we need to have a process where all the elements are in balance. I have a machine tool, I have a tool, I have a workpiece, I have fixturing equipment. All of that needs to be brought together in a balanced form so that everything is under control. And in the end, the result of the operation is, as I already said, a correctly finished workpiece, quality, at a certain cost, within a certain time. And that is the model how we work with machining. Some people call it a machinability model, but that's perhaps a bit discussion with words. It's a model where I say, okay, I have a process and I have a cutting tool. I have a workpiece and a cutting tool. I bring the two together and there needs to be balance. Balance in all respects. And that's what I try to show here with the middle thing. There must be mechanical balance, thermal balance, tribological balance. Everything, all these phenomena needs to be well balanced. And there are variables influencing those phenomena. Some of the variables come from the process, here in this picture from the right. And those are going to, to put a load on the cutting tool. A mechanical load, a thermal load, whatever. And the cutting tool, the right side here in the picture, has a certain ability to carry that load. And that's the balance I need. The carry capacity of the tool and the loads acting on the tool needs to be in balance. Because if the loads acting on the tool are bigger than the load bearing capacity of a tool, I have unbalance, I have technical unbalance. The result will be a badly functioning tool. The result will be a broken tool. And if you have a broken tool, you have a destroyed workpiece, or in quality, or in costs, or in time. So there's unbalance. There can also be a different kind of unbalance, because some people think, yeah, wait a second, I'm going to do the smart thing. I take a tool with a very big load-bearing capacity, so I'm safe. And it's a fine approach. However, we have to realize that mostly a tool like that is, from a purchasing cost perspective, more expensive. And then the question can be asked if we don't have an economical unbalance, that we are using a tool which is too good, between brackets, expensive, for the operation we want to have. So it's all about this model. And the situation is today still, if I work with this model, if I try to figure out which tool to use, cutting conditions, machining strategy, to have a balanced situation, and people ask after a while, okay, did I do a good job? Did I manage to create a well-balanced situation? We kind of fall a bit back on intuition-based thinking. We ask the operator. How was it? How was the operation? How were the ships? Didn't you had vibration? That type of stuff. Or a little bit more objective, because asking the operator, it's a subjective approach. A little bit more objective is looking at the used cutting tools, because if you know what to look for, a used cutting tool, a used cutting edge, once shows things. So the evaluation, did I do a good job working with this model, is objective, subjective. Ask the operator, look at used cutting tools, where hopefully a future, and not so far away future, will be that I can do the data driven machining, that I have my, perhaps somewhere in the future, in-process measuring of things to see if things are indeed well balanced. Workpiece materials play a very important role in this. Quite a lot of work has been done to find out what are the real properties now, a workpiece material, or the properties from a workpiece material that have an impact in how a cutting process goes on. And if you have your machining model and you understand what it is, and if you have your insight in your workpiece material properties, you can bring the two together and you can start thinking, okay, I want to have mechanical balance, I want to have tribological balance, I want to have thermal balance, which means that I don't want to overload the tool. And that can be translated into constraints. And constraints is sounds negative, but it's not negative. It's just a line, a border that you should respect, not to overload the cutting tool. To have a safe operation, a reliable operation, and that's if you think on it, reliability is key, because I want a correctly finished workpiece at a certain cost in a certain time. To make it happen, that total picture, I need to have a reliable process. And that is one other way to define a machinability model. It is a model that helps me to find out where the constraints are. And once again, constraints is not negative. Constraints is, I don't know another word, borderline or whatever, that you have to respect during machining. And if you stay within the constraints, the process will work fine. And we have what we want in a very objective way. And it's not about I think, I hope, I suppose, but it's about I know. And that is the whole target of the exercise. Now, in this creation of a model, in this creation of a domain in which you can work and have a reliable process, there are mechanical things to consider. One of the things to consider is ship formation. And ship formation is perhaps, that's still a frontier in my eyes, because if you look to ships, in reality, in a workshop, every single ship is different. And I think that's really a challenge. I still think we don't fully understand how a ship is formed. Otherwise, we should be capable, much more than the present situation, to control our ships and to avoid problems, as you see behind me, that are daily life in a workshop. Ship formation, it's about having ships of a good form, of a correct form, so they don't disturb the process. They allow the cutting tool to work. They are not putting in danger the quality of the workpiece, the safety of the operator. That is the definition of a good ship. And good ships, it's heavily depending on the workpiece material. I think you all know that. Workpiece materials, some of them give short ships, whatever. Others give long ships, whatever. And it's also depending a lot on which tool you use. Especially the geometry of the tool plays a very important role, and cutting conditions. And that's the battle here. Better understanding as we do today, so we can bring more uniformity in the type of ships we form. We can take out a bit of the chaos factor out of ship formation. Mechanical is also cutting forces. I think a lot of you are rather familiar with what we refer to as the Kinzel modeling. There are quite a lot of models we use to describe cutting forces, the forces that we have to put on a tool so the tool can move through workpiece material, deform it, shear it off. Kinzel still today, it's 50 years old, or it's 70 years old, but it still gives rather good results. So it's a rather good thing, and we need this because the cutting forces, some of the practical issues we have during machining, problems with quality, with vibrations, with broken tools, and so on, can be brought back to there is unbalance in cutting forces. We need to do something. And what the Kinzel approach then describes is the variables we have to work to change cutting forces. To influence their size, to influence the direction in which they work. And there is even, and I don't want to frighten you away with this formula, because the reality of today is that we don't work with these things anymore. We have much better aids at our disposal for this. But I want to show you the formula, because there is in this formula the first symbol there, CV, that's what is referred to as the variation factor. And the rest of this formula, and a formula is just a symbolic writing of an insight, the rest of this thing we fully understand. We understand the relation between cutting conditions and forces. We understand the relation between geometry and so on. But if we measure, we still see differences. And so far, scientists, they say, okay, the differences we put in that one single factor, psi v, the variation factor called. And quite a lot of research today is done on that variation factor. If we have a reality, if the model predicts something and we see in reality that there are differences, the big question is, in that variation factor, what is the variable creating the difference? That is what people work quite a lot with. You remember perhaps one of the Getting Technical live events, we talked a little bit about this, and we said there is not one single cutting force, but it's a variation of cutting forces, because it's due to ship segmentation that cutting forces go up and down. That's a very typical example of something which is in that psi, in that variation element in the Kinzel model. Thermodynamics. We deform material. If we deform materials, heat is generated, and that heat that translates into higher temperatures in the tool, in the workpiece, in the ship, and there are consequences to that. Now, if we try to model it, what we have is a situation where partly we deform material and partly there is kind of a friction between a ship and the rake phase and a workpiece and the clearance phase. Mainly the sharing off zone is generating a lot of heat. To a lesser extent, it's also the friction. Heat is being produced, and heat has a natural tendency to spread out. Part of the heat goes to the workpiece, part of the heat to the ship, part of the heat goes in the cutting tool. Now, heat that goes to the ship is for us very good, because it means the heat goes away from the process without doing any harm. Heat that goes into the workpiece can modify the workpiece properties, deform it, expansion, the structure changes, so we have to be careful with that part. And heat that goes into the cutting tool has consequences, because if we look to this process, and if we look to temperatures, first of all, a very important thing, because everybody talks about the cutting temperature. Well, there is no cutting temperature. There is a cutting temperature gradient. There are different temperatures depending on where you look and when you look. Do you look at the situation after 1 second cutting, or do you look after the situation after 5 seconds, or after 5 minutes, or 50 minutes? And each time you will see that there is a different picture of temperatures in the cutting tool, in the workpiece and the ship, but once again, the ship is of lesser concern for us. And it's intriguing, because if you look to the rake phase, and on a rake phase we see different types of temperatures, and that is what I try to show there in the diagram, that at the cutting edge itself, you have a certain temperature. As you move away from the cutting edge, the temperature increases, and if you continue to move away, the temperature is reduced again. The same we see on the clearance phase. We see on the clearance phase, on the surface, there is not one temperature, but there is a temperature gradient, a difference. At the cutting edge temperature, you move away from the cutting edge, temperature increases, and if you further move away, it reduces again. You see each time 3 lines here, that's for 3 different cutting speeds. So whatever cutting speed, this thing reproduces. And interesting is, if you look to a worn cutting edge, where the temperature is highest, you have most wear after a given amount of time. So there is in machining a very clear relation between temperature and wear. And this picture, personally, I find this one of the most exciting pictures in machining. This picture tells me, depending on a certain temperature, and remember we have different temperatures along a cutting edge, on a rake phase and a clearing phase, which physical phenomena will be the main reason, the main source for wear appearing on the surfaces. And that brings me to the tribological dimension. There are 4 mainly for physical phenomena leading to wear on a cutting edge: abrasion, scratching effect; adhesion, the build-up edge thing. I'm pretty sure you are familiar with. Fatigue, the hammering effect on cutting edges; and chemical. We bring together different materials in rather high temperature zones with high pressures. Also, chemical reactions will take place. So there are different phenomena. How the wear develops, the pace of the wear development is another variable. And if I bring the two together, which type of physical phenomena leads to wear and how fast does it lead to wear, I end up in what we call the tribological models in machining, describing how wear will develop on a cutting edge over time in a given situation. And there are quite a lot of variables to take into account here. And if you look again to reality, and if you take, most probably you in your workshop, you also collect already used tools for reconditioning. But if you look in those bins with the used tools, and if you look at cutting edges, you see that roughly every cutting edge looks different. And so to apply this modeling, we need structured approaches. And one structured approach is what we call global tool deterioration management. It's the subject for the next two sessions we are going to organize. Because if you control this, everybody or a lot of people think that wear in machining is a technical thing, and it is. But wear in machining, when well worked with, can also be a management tool. Can also be a management tool to influence what people refer to as operational excellence. But I'm not going to talk too much here because time is flying already, I see. The next session and the session after, we are going to focus only on one single thing: global tool deterioration management. How to work with wear on tools in a way that it can become a management tool to take certain decisions to improve the operational excellence of a workshop. Tool life dimension: if you have wear, what you see here to the right is how wear develops on a cutting edge. This is not computer animation, this is rather old pictures, that's why it's in black and white. You see how wear develops on a cutting edge. And a question that poses after a while, and there was one gentleman 100 years ago, a little bit more already, Taylor, an American, who was focusing on the speed with which this develops, this wear. Can I influence this? Can I control it? What are the variables? And that is what we know today as Taylor's law or Taylor's model to describe tool life. And tool life is defined as the useful lifetime of a cutting tool, the time the tool can work and delivering on expectations. That's tool life. And what Taylor noticed was that mainly a cutting in a given situation of a tool and a workpiece, that the cutting speed is a very important variable. So he focused quite a lot on cutting speeds, and he focused on a situation where he could control it. And that thing, and you have, if you see the picture here, you have to be aware of that Taylor is a model that works within a certain window. If you are out of the window, this model is not working anymore. We need other approaches. But this is, I think, if you call yourself a machinist and you don't know about the picture here, the formula is less important. Taylor says there is a relation between cutting speed and tool life for a certain type of wear, and so Afterwards, people, of course, dive much deeper into this, and they figured out it's not only cutting speed, it's also the tool cutting material and the cutting geometry and the feed and the depth of cut. So Taylor's original thing was extended to a much bigger thing. And again, here the formula, I show the formula, not for the formula. We don't work with that anymore. We have much better things to do, to work with today. But also here you see, and after rather big discussions, the scientists said this Taylor thing, we can continue to work with it, but we have to add that variation factor. Here you see it in the middle, the psi v, because we have a model, we work with it, we predict the tool life, we look to reality, we see reality is different. And then the question is, okay, what did we overlook? What variable is causing this? And all of the potential ones are put in that one single psi factor, the variation factor, where quite a lot of research work nowadays is focused on how can we give it a value in certain situations. You have also the techno-economical model. I added here just to be complete, because if you look to machining next to the technical side, of course, there is an economical side. We do machining to produce workpieces with certain demands on quality, on costs. We want to work with minimum costs. So we have an economical sustainability. We are competitive on the market with the products we produce. What people have to realize, I call it the next step in economic machining, is that the costs in machining are not only related to the process, but are also related to the things around the process. I mean, if the result of your operation is a not correctly finished workpiece, you need to produce another one. That's an extra cost. If your machine is standing still, not making any workpiece, and it's standing still for certain reasons, there is a cost related. And these two extra costs, due to lack of quality, due to time efficiency, also need to be carried with the one workpiece in the end you produce. With other words, what I try to do here is link machining to process efficiency. And I use here the example of an OEE split. Some of you, or perhaps all of you know what OEE is, the overall equipment efficiency, where we look to time spendings. And what we see, if we look to the average machine tool, a lathe, a milling machine, is that next to actual machining, what you see here as the running time, we also spend time on setting up the machine. We also spend time on problem solving. We also spend time on unforeseen things that happen. And one reason why we need to go from intuition-based to model-based machining, my belief, is if I want to increase the efficiency of the total picture, if I want to have lesser stops and speed losses due to the process doesn't do what I thought it was going to do, I need to be better in control of the process. Just to give you an example, you see here two situations in one. One situation is in the middle. It's a real situation. It's something I had myself a couple of years ago, where I was working in a workshop on. In the middle, you have a situation where 15% of the time the machine is actually producing workpieces. The other situation, the situation around it, is the machine is producing in 50% of the cases workpieces. Now, if we talk about optimizing, these are two very distinguished, different situations. Optimizing the total picture for the situation in the middle is first focus on the things around the machining process, because they stand for 85% of the time. optimizing the situation for the situation on the outside of this circle. There you can say, okay, machining stands for 50% of the time spending. It's worthwhile spending time on optimizing a machining process because it's a big part of the total time already. Model-based machining, very short. But as I said, we have the reference material. And of course, if you have questions, if you have remarks, if you want to continue a discussion on this, I find this exciting. So please put comments in the chat. Let me know. We can continue to talk about this. A few words on sensor-driven machining. Because I think from an historical perspective, already Taylor, because if you look to the book he published, where he described what we still call today the Taylor equation or the Taylor model, 1906, he already said, and I most probably, I suppose, you can't read it, so I make it a bit bigger. Taylor said, okay, I have the mathematics, I have the formula, but if I take the formula, give it to mathematicians, they come back and they say, you have an impossible formula. There are much too many variables. We can't solve it. And that's why for a long time, intuition-based machining, we knew the model, but we had to count on the intuition of people to solve the equation. Well, today, and now I'm dreaming perhaps, but can you imagine that we have enough data collected over time that in a more structured way we could solve Taylor equation? The moment we and it's just an example, I simplify, but the moment we can do that, we have digital machining. And Taylor already he was in that respect kind of a visionary. Already more than 100 years ago, he said we need something. In those days, it was an experienced operator. Today, we have other possibilities. There is only, it's a numerical method we need to find to solve the equation. It's data we need. Which brings me to data-based machining, digital machining. If I have the models, if I have enough data, so the data is representative, is relevant, is meaningful, then everything comes together, and then the picture is, or the circle is round, I should say. Machining is a process where there are, from a physical perspective, quite a lot of things happening. Mechanical things, thermal things, tribological, chemical, and so on. What we want with model-based machining is to describe this thing with a model, so we can use this model to create a balanced machining operation. A balanced machining operation where we know, with a minimum of trial and error, with a minimum of efforts, with a minimum of waste, with a minimum of time loss, that we know that the result will be what we want, that correctly finished workpiece and so on. Knowing how good we did our job in working with this model, today we still refer back to, as I said, we talk to the operator. One step further it's more objective. We look to used cutting edges. How we could do that, what we could learn for that, that's for the next 2 sessions. We are going to dive into those in that aspect then. I showed you 2 formulas. Twice I said, don't worry about the formulas. In the modern world, we don't work with these formulas anymore. It's too time consuming, but today we have apps, we have software, we have whatever that takes care of the mathematics. For me, important, and I think that's the new role of the modern machinist. It's not about calculating things. For that we have our iPhone or whatever. It's about taking the results of the calculations and interpret that. What does this mean? How do I work with that? Does it seem logical for me? And most important, of course, if it's put in practice, in reality, then observing and seeing if reality follows the model, and if not, correct. I think that's the role of a modern machinist is not being a calculator, it's being an observer and a corrector. Observe what is happening and, if needed, correct. I'm a bit proud on myself. 45 minutes, and yeah, perhaps I'm too fast by saying I'm proud on myself, because I should ask you first: is the picture, is the story, does it make sense? Despite we went so fast from point A to point B, please let me know. Put it in comment. It's useful for me to know if I didn't jump here and there too fast, too far. Anyway, again, I repeat. If you want a copy of this presentation, if you want to have information on all the technical books we have around machining processes, I underline these are technical books. These are not guides or something. It's really more the scientific approach to machining, which we explain in these books. Just let me know. With pleasure, we will inform you about this. Do we have questions? And for that, I check to see. There are a few questions, and I see we are also good in time. One question is, somebody says heavy machining or micro machining is different applications, but we use different tools. So it means that for both we can use the same model. Right? Question mark. That's a very clever question. One could say, from an intuitive aspect, if you have heavy duty or micro, already you should say, yeah, I need different tools, very obviously. So you start with different tools in the applications, different applications, and then you see that roughly, the model, you can work with one model indeed. However, another answer could be, wouldn't it be nice if we have one model, and if you use the model, automatically you find out that you need different types of tools. Or automatically, that based on the model, you find out that for this application you need that type of tool, and for another application you need that type of tool. So this is a bit, this is, the chicken or the egg, Is it because we use different tools based on our intuition, that we can say, okay, it works, the model we have works? Or should we better say, no, I want the model, and if I apply the model will tell me that I need different tools in different applications. So I don't have an answer here. It works in two directions, I could say. Another question: intuition-based machining, is that the same as manual machining? No. Very often on a manual machine tool, on a manual lathe, on a manual milling machine, which is the older type of machine, and I hope that some people now won't say, yeah, but mine is new. I mean, historical, the older machines were manual operated, and the operator was using his intuition to do that. But it's not the same. Manual machining versus CNC machining is how is the machine tool controlled, and intuition-based machining or model-based machining is how do we approach the process when we need to select strategies, tools, approaches, cutting data, and so on. Time allows. Is a coating influencing ship formation? Yeah, that's. I would say yes, But that's a very, no, I should say yes, no. Because we see in some situations that it does influence ship formation, both in a good manner or a bad manner. And in other situations, we don't see any influence whatsoever. That's a very typical example of something that is today still in that psi factor, that variation factor. There seems to be something, but we still don't see the picture very clear. So my answer is yes, no. Is the pace of wear development depending on the temperature? Yes. The very general answer is the higher the temperature, the faster we see in general that the wear will develop. But I have to be a bit careful here with answering because the wear on cutting edges, it's not only the maximum temperature, but it's also the temperature gradient that influences a lot. So perhaps it would be more correct to say that the pace of the wear is influenced by the size, the magnitude of the wear gradient, the difference between maximum and minimum, and how fast it changes in time. What is global tool deterioration? Yeah. I suppose the problem here is the word global. What tool deterioration, I suppose everybody understands. Tool deterioration is a phenomenon that describes how a tool loses over time its ability to function well due to whatever phenomena. Tools wear out, tool gets dull, tools break, things happen, and the condition of the tool deteriorates. So that's tool deterioration. With global, what we mean is that if you go back to mass production, in mass production, tool deterioration, tool wear more, I would say there, is something we are rather well under control of. Because in mass production, the working conditions, the cutting conditions, the cutting data do not change. It's always the same, year in, year out, by means of speaking. The only variations we can have that are meaningful are properties of workpiece materials. That can create some variation, but in general, tool wear in mass production after the initial testing, but that's another discussion, because initial testing, it seems in mass production, we use intuition-based machining principles. We trial and error. But as I said, that's another discussion. But we have it rather well under control. If you have seen one cutting edge, you have seen them all. If you are in a situation of small batch production, especially diverse work, different workpiece materials, different workpieces, big, small, what you see is that one cutting edge, if you look at it, it doesn't say anything. You see one cutting edge that has been used in a number of situations, but the next cutting edge is in another situation. So if you look to tool deterioration, tool wear, you need to widen your view. You can't focus on one cutting edge only. You need to have a more global view on all cutting edges. And that is the underlying meaning why we talk about global tool deterioration. It's not based on one only, but on all of them over a certain period of time. And we try to learn something from that. But as I said, that is for next time. Yeah, we still have time. What's the Archer model? Archer was a scientist who described if you have gliding wear, if you have two surfaces which are in contact with each other, and there is a certain pressure and there is a certain contact temperature, and the two move compared to each other, what we see is that this phenomenon creates wear on the surfaces. That's the definition of wear. And Arshert was studying that phenomenon and found out that if you have certain types of wear, it's possible to predict after a certain amount of time how much damage you will find on a surface if you have pressure, temperature, movement. And the description of what he found, that is what we refer to as the Archer model to describe wear and wear development. Yeah, we have time for one question more. What is KC11 and MC? That are two factors we use in the Kinzel approach when we want to describe cutting forces. KC11, the symbol KC11, the unit is Newton per square millimeter. We call it, there are different groups or different schools here. Some call it a specific cutting force, others call it a specific cutting pressure. The unit is Newton per square millimeter, so it's a pressure, but anyway, that's not so important here. It's the cutting force, the tangential cutting force, the main cutting force, the cutting force that will act in the direction of the cutting speed, that you would measure in a certain material, so it relates to a certain material, and you use a certain cutting tool. The cutting force that you would measure if the feed is 1 millimeter and the depth of cut is 1 millimeter. It's kind of a material constant, like a material has a certain density or structure. Every material also has, within a certain window when being machined, a certain specific cutting force. It's an indication for how big the mechanical loads will be on a cutting edge. MC is an exponent in the Kinzel formula. MC is a mathematical way of saying that the relation between feed and cutting forces is not linear. If you take a cutting speed and if you have a cutting speed and you measure a cutting force and you increase your cutting speed with depth of cut, you increase your depth of cut with a certain amount, you will see that the cutting force follows more or less to the same amount. So there's a linear relation between depth of cut and cutting force. If you would do that same exercise with feed, if you would start to increase your feeds and you would measure cutting forces, you would see that as feeds increases, cutting forces go up, but not to the same extent. Especially when the feeds are getting bigger and bigger and bigger, you see that cutting forces still increase, but relatively seen, not so much anymore. It's based on that phenomenon that we know today, a machining process we refer to as high feed machining, where we on purpose kind of look for high feeds as the road to productivity, but in situations where we have to be careful with the cutting forces during the process due to instability or whatever. That is that two values, KC11, specific cutting force, and the exponent, we call it the Kinzel exponent, MC. But I see, we have we have time for one extra question or one more question. All the other questions I see here, I answered them in the comments or we send me a mail or something and I take care of them afterwards. The last question then, does reliable machining easily apply today in a machining process? I say yes. But I'm a bit careful now because I work with this since a big number of years. And for me, it's kind of, I I suppose you in your company, you work with SOPs, standard operating procedures. Well, one standard operating procedure could be the description of, in a certain workshop on a certain machine, what would be the window in which we have reliable machining. It's an exercise to be done just once and you have it. But as I say, I'm a bit careful with saying yes, because for me it's daily work kind of. And I do understand if this is the first time you hear about this, that you could have doubts about, is this easy? Yes, no. But the one who asked this question, if you want, we can continue the discussion afterwards, and I can give you some tips and some tricks on how to put it in practice in an, believe me, really very user-friendly manner. It's not going to be perhaps 100% scientific, but believe me, it's 100% technological. It works and it gives good results. Seen the time. I stop here. All the other questions, again, a promise from me, I'll take care of afterwards in the comments. I want to invite you for the next session, 30th of April, where, as I said, we are going to dive into that tool deterioration thing, and not the traditional way. You know, everybody talks about, if you have this type of wear, you need to do this, and if you have that type of wear, that's the approach in mass production. I want to take the approach in small batch production, where, if we are clever, tool deterioration, next to the technical dimension, also has a management dimension. If we work well with it, we can use this to work with operational excellence principles. But as I said, that's for next month. Hopefully, if you are interested, I see you back there. Thank you very much again. Thank you to my colleagues for assisting to make this possible. It was a pleasure talking about this, meeting you, even if it's virtual. Take good care and hopefully see you next.